Today, our study will journey into the realm of the solubility product constant, or KSP. This is an equilibrium constant which measures the solubility of ionic solids. Its value equals the ion product of the dissolved species in equilibrium with the solid. Now note, undissolved solids in their standard state have unit activity and so do not appear in this equilibrium expression. And introducing the star of this show, lead iodide, also known as PbI2. As you can see, lead iodide is yellow, really yellow, and rather dense. But remember, above all, it is toxic. It's probably a lousy movie which gives away the plot in the first scene, but here it is, the whole experiment. You'll start by making 5 mixtures of lead ion and iodide ion of known stoichiometry. Next, you'll make iodide ion standards. These are solutions of known concentration. You'll oxidize all of these so that the colorless iodide ion is converted to brown iodine solution. And you'll measure the light transmission in a spectrometer. Using the data of the standards, that is known concentration, you will prepare a standard plot, that is absorbance versus iodide ion. This should be a straight line if it follows Beer's law. From this standard plot, you will read the iodide ion concentrations in the solutions made in one above. Finally, you will calculate the KSP of lead iodide in the 5 solutions made in step 1. Now remember, all of these KSPs should be the same, and they will vary only by experimental error, and they should vary only slightly. The solubility of salts at a given temperature can be affected by several factors. One of these is called the common ion effect, and another is called ionic strength. The common ion effect, that is, dissolving additional amounts of one or more of the ions forming the salt, will decrease the solubility, as predicted by the principle of Le Chatelet. Ionic strength, that is, dissolving any ion to increase the total concentration of ions in solutions, increases the solubility of the solid. Let's take an additional look at these. At equilibrium, a solid in solution is dissolving and precipitating at an equal rate, so there is no net change in the solution concentration. Adding a common ion, here iodide ion, increases the rate of precipitation. This increased rate continues until the ion product of the lead and iodide ion concentrations again equal KSP. That is, until the system reaches equilibrium. This new equilibrium has precipitated additional lead iodide. As for ionic strength, the solubility of an ionic solid in aqueous solution is assisted by the water. The water helps disperse the ion's charge. Solution can also be assisted by an ion of opposite charge, which will form a neutral ion pair in solution. So increasing ionic strength increases solubility. You can also use the principle of Chatelet to explain the increase in solubility, even though it doesn't sound reasonable. Although not shown, KSP is really the equilibrium constant of aquated ions with the solid. The increase in ionic strength removes some of these aquated species by forming ion pairs. The decrease in aquated ions in solution leads then to the additional dissolving of solid as predicted by Le Chatelet. All solutions used or made in this experiment will have constant ionic concentration of potassium nitrate to maintain constant ionic strength. The higher the ionic strength, the more soluble is lead iodide. We will determine KSP by making solutions in equilibrium by precipitating lead iodide, starting with solutions of lead and iodide ion of known concentrations and volumes, and also by starting with pure precipitated lead iodide and dissolving it. A word of caution. In this experiment, do not confuse potassium nitrate, which we'll use to maintain constant ionic strength, with potassium nitrite, which we'll use as an oxidizing agent to convert the colorless iodide ion to the brown iodine in solution. The nitrate ion has a nitrogen in the +5 oxidation state and is planar. The nitrite ion is a V-shaped ion with its nitrogen in the +3 oxidation state. In oxidizing iodide ion, the nitrite ion is reduced to gaseous nitrogen. To start this experiment, you'll make equilibrium solutions and allow them to stand, usually overnight or longer, to allow colloidal particles to coalesce and settle. You'll make pure lead iodide and dissolve it in your potassium nitrate solution. This approaches equilibrium from solid to solution. The only information we need in this experiment is the equilibrium concentration of the iodide ion in solution. So, we make pure lead iodide, dissolve it in hot potassium nitrate, bring the solution just to a boil. Now collect the solution of dissolved lead iodide and allow it to cool. Note the slow crystallization such as this produces larger and usually very pretty crystals. You will now make solutions starting with known amounts of lead and iodide ions of known concentration. These solutions will precipitate lead iodide. Remember, you will need to know initial concentrations, initial volumes, as well as the final equilibrium concentration of iodide ion. You will pipette out the exact volume of lead ion using a 5 milliliter pipette. Rinse this pipette with the lead solution if necessary before using. Fill to the mark, then start collecting using gravity. Finally, touch the pipette tip to the side to finish the collection. You will measure out the iodide ion using a graduated pipette. Again, rinse it before starting if necessary. Fill and bring to the mark. Here we miss 0, so we'll start at 1. Now make sure you start and stop the collection. The amount you pipette out is the difference between the number that you started at and the number that you stopped at. Finally, we'll add 2.50 milliliters of potassium nitrate solution. This will make a total of 10 milliliters of solution. Now remember, all solutions which we'll make here are using the same potassium nitrate solution, so the ionic strength throughout this experiment is constant. Since we'll let the mixture sit and settle, we'll cover it with parafilm so it does not evaporate. Now in using this, stretch the film as you cover the tube and make sure you cover the tube at least twice as you stretch the film over the top of this tube. With our KSP and standard solutions made, we are now ready to measure our iodide ion concentrations. We will do that by oxidizing the colorless iodide ion with nitrite ion to brown iodine under acid conditions. We will also use the cuvette as a volumetric flask. We will measure percent transmission using a spectrometer and blue or green light. Use percent transmission of the blank in our sample. We will convert to absorbance. This absorbance will be related to concentration using Beer's law. We will now make and measure one of these standards. Using a graduated pipette, rinse if necessary, and fill with the 30 millimolar potassium iodide solution. Add the potassium iodide to the tube. Again, remember, using our graduated pipettes, you must start and stop to deliver the amount you want. So the difference between the numbers you started at and you finished at is the amount you delivered. Don't forget, touch the tip to the side. Now we'll dilute by adding 5 milliliters of potassium nitrate from the burette. Since the total volume is 8 milliliters, the concentration of this standard is 11.25 millimolar. We will measure our iodide ion concentration spectroscopically. To do this, we'll use a 10 centimeter sample tube as a cuvette. Pipette into the sample tube 5 milliliters of potassium nitrite solution. This is the oxidizing agent. Acidify with 2 drops of 6 molar HCl. And finally, add to this mixture the computer-assigned volume of our iodide solution. Here we will be adding exactly 3 milliliters. To do this, we will use a graduated pipette, rinse of course if necessary, and fill. Touch to the side, then collect. Remember, you must start and stop the collection when using a graduated pipette. As you can see, the iodide is converted into brown iodine by the oxidation. We will use the same cuvette throughout this experiment and use the same volumes each time, so it is convenient to convert our cuvette into a volumetric class by marking the bottom of the meniscus at this point with tape. As you can see, nitrogen gas bubbles have formed in the reaction. Tap the cuvette gently on a resilient surface to dislodge these bubbles. Now measuring this in the spectrometer, remember you must always set this dumb machine so it reads 0% when no light is passing through and 100% when the light is passing through distilled water. In reading, be careful to prevent parallax error. The bottom half of the cuvette must be clean and free of bubbles. To free the bubbles, tap the tube gently. Be careful not to break the cuvette, and then check again for any bubbles. Read the spectrometer. If you can see the reflection of the needle in the mirror, there is a parallax error, so move your head or close an eye. Having made and measured our standard, here is the Beer's law plot of absorbance versus concentration. Note, it's a straight line which should go through 0. And this is the point we just collected. The spectrum of iodine in solution shows a maximum of about 455 nanometers. Now in this video, we are collecting data at 525 nanometers. Make sure that you follow the directions and use the correct wavelength. Since we'll be diluting to volume with our solutions in not water, it is best to rinse and dry the cuvette between measurements. So, again, we'll add 5 milliliters of potassium nitrite solution. Touch the tip of the pipette to the side to finish the addition. A couple of drops of HCl. Dilute to volume by adding the solution with a Pasteur pipette. Be careful to add only solution, absolutely no solid. In transferring, be careful not to stir up the settled precipitate. Centrifuge if necessary. Mix and measure in the spectrometer. Again, make sure there is no parallax error in the reading. To determine iodide ion, draw a line parallel to the bottom of your standard plot at the measured absorbance. Then drop a perpendicular where this line crosses the standard plot. Again, make sure the top and bottom of this perpendicular are at the same concentrations. Finally, we'll do a couple of calculations. Starting with the lead and iodide ions to form precipitate, we must know the exact amount of volume of each. Measuring the iodide ion left in solution by spectroscopy allows us to calculate the amount of lead iodide precipitated. This then allows us to calculate the lead ion solution remaining in solution, and since we know the total volume of our solution, we can calculate KSP. We've collected the following data for equilibrium based on starting with pure lead iodide. Here, the amount of solid is not critical, only that some solid be present at equilibrium. The iodide ion concentration is obtained from the spectroscopic data, and the lead ion concentration should be obvious from the equation above. This leads directly to our KSP value. So now, back for its final curtain call is the star of this show, and so lead iodide and I bid you goodbye.